Hey everyone, StatsGuru here. Welcome back to the channel. For those of you who may be new, welcome. Today I want to walk through the chi-squared test, walk through some examples of that, and just give a little background as to when this is used and how it's used. So yeah, let's just jump right into it. So the chi-squared test is typically one version of a hypothesis test. So this is going to be using the null. So we have our HO and we have our HA. So we're going to have our null and we're going to have our alternative hypotheses. So we need to make sure that we understand what's going to be the null and what's going to be the alternative. When working with the chi-squared, it's typically denoted as a big swoopy X with a little squared on top like this. So this is the Greek letter for chi, and the formula for the chi-squared test is it is going to be the sum of our observed value minus some expected value. We're going to square that, and then that's divided by our expected value. So this is a typical formula for the chi-squared test. When using the table in the back of the book, we do have degrees of freedom, and that's going to be n minus 1 degrees of freedom. So this is what the chi-squared test looks like. This is how it's typically denoted in statistics. And again, we're looking at our null and alternative hypotheses. Some examples, just to sort of get the ball rolling with this, could be a heads or tail flip of a coin test. So we're counting the number of heads, we're counting the number of tails. So we have an observed and then an expected value. We expect this to be a 50-50 chance, right? So then we go through and we count these things. So that's kind of how the chi-squared test can be started to be thought about. Is we're expecting one thing to happen and then we're visually inspecting or observing what's actually happening. So with that, let's just jump right into our first example. So for our first example, we're given a plant has two alleles. They have a green allele, which is the dominant allele, and then they have the purple, which would be the recessive. So we crossed two parent plants. We planted 148 baby seedlings. We noticed that 88 were green and 60 were purple. So we want to figure out what's the chi-square value, and we want to test to see if the plant, one of the green parent plants, was heterozygous. So what do we know? We know that a parent plant can be a GG, or it could also be, capital G, lowercase g. In both cases, this is going to produce a green plant because we know that it's dominant. So the only option then would be lowercase g, and that would give us purple. So when I'm doing chi-squared practice problems, I try to write down the information that I'm given, and then also any other relevant information within the question, such as anything involving the numbers, so that we have a clear understanding of what we're looking at. So when we are going to do our hypothesis test, okay, so we have our null hypothesis. Well, what does this say? Well, this is saying that the parent plant is one of those two. So we're just going to simply do it like this. So we know that this is the parent plant. Our alternative hypothesis would be that it's not equal to this, right? So it's not equal to that, and it is equal to that. So we're going to test those two things, so equal or not equal. Where do we start? Well, let's start by making the allele table. So we know that a parent can be a G like this, and we know that it would be lowercase to get a purple. So we have GG here, we have GG this way, and we have upper and lower, and then again we have lower and lower. So from this table, we can expect a 50-50 split. So this is what we're expecting because we're testing to see if the parent was heterozygous, right? So that's where this upper and lowercase g come from, meaning that it's not a double dominant, right? So this is a no-go. This is what we're looking for. So if that's true, we're expecting 50% of our plants that we plant to be green and then purple. So if we wanted to write this out, we know that there were 148 seeds, okay? And then from the 148, we would expect there to be an even split. So there should be 74 and 74 of each. In our case, we had 88 and we had 60. So if we were then to transform this over to a chi-squared, we have the chi-squared formula, which says we're going to have the sum of our observed minus our expected. So we have 88 minus 74 squared, and that's divided by our expected. And we keep doing this for the things that we have, so then we also take 60 minus 74 squared minus 74. So this, when we figure out this, is equal to 5.30. So that is using the chi-squared formula. And we know that degrees of freedom, if we were to write out our degrees of freedom, is based upon the hypothesis. So we have 2 plants, and we minus 1, so this is equal to 1, because we have 2 plants were crossed together. So that's the n that we're using for this. So we know that our chi-squared value is 5.30, and we have 1 degree of freedom. Let's jump over to the chi-squared table to find our critical value. So here we have the chi-squared table. We know that we had 1 degree of freedom, and our alpha value was 0.05, which I don't think I wrote down, but that's the typical 0.05 alpha value when hypothesis testing. So we have a critical value of 3.84. So let's hop back over and we'll show you what this looks like on the chi-squared chart. So we have our chart. So if we draw the chi-squared distribution, it's not a normal distribution. It kind of has this weird tail to it. We don't need to get into the real deep mathematical reasoning why. We just need to know that our value is, from the table, 3.84. So anything that is beyond this value is what we call the rejection region. If anything falls within the rejection region, we can reject the null hypothesis and conclude that there is enough evidence to support the alternative. So 3.84, and we had a value of 5.30. So that checks the box, which means we can reject the null hypothesis. So our conclusion is, so we reject the null hypothesis and conclude that there is enough evidence to say that the parent plant was in fact heterozygous. So that is what we were testing. We used the chi-squared test to do that. We found our rejection region value. We found our chi-squared value from the formula. And it turns out we can reject the null hypothesis and have something interesting saying that yes, there is enough evidence to say that our parent plant was heterozygous. So that's the first example. Well, let's go ahead and jump over to one more example. So in this example, we have a regular die. We're going to roll it 300 times, and we're going to test that we're going to get an even distribution of 1 through 6. Right, since our dice is even and we roll it 300 times, we would expect all of the numbers to eventually come to an even distribution. So if we were to draw this on a table, we have our numbers 1 through 6, 4, 5, 6. And in this case, we expect it to be an even split of 50 of each number, and that would give us 300. So that's what we expect to happen. What we actually observed to happen was the following. We had 38 here, we had 54, 62, 21, 70, and 55. So this is actually what we ended up observing. So our hypothesis is that there is an even chance for each number, and the alternative would be that there's not an even chance. So this is what the hypothesis is set up as. We have an equal chance, we do not have an equal chance. So when we calculate our chi-squared value, we use the formula, which says we're going to take our observed, so 38 minus 50 squared, and we're going to divide it by 50, which is our expected value, and we're going to do this for each and every observation. I've already calculated this ahead of time. This gives us a chi-squared value of 31.40. So that is our chi-squared value. And we have degrees of freedom, which is 6 numbers in our left-hand side. So it's 6 minus 1, which is equal to 5. So let's jump over to the chi-squared table and find our critical value. So we have 5 degrees of freedom, and we know that we are at a 0.05 alpha level, which tells us our critical value is 11.07. So if we draw our chi-squared curve, the critical value was 11.07, which means anything beyond that is the rejection region. And our calculated value turned out to be 31.40. And we can conclude that we are going to reject the null hypothesis and say there is enough evidence. So there is enough evidence to conclude that our dice was not even when rolling, or something like that. So what we're basically doing is we're testing if this dice is actually even, or this die I should say. Turns out, based upon our observations here, right, and using the chi-squared test, we can reject the null hypothesis and say that it wasn't, and that's supported through our evidence. So it's very fascinating. I do have one more example lined up, so let's go ahead and take a look at that example. Okay, so we have a bag of marbles, everyone's favorite type of question, I'm assuming, with 5 red, 3 yellow, 3 green, and 1 white ball. So we draw one at a time and we put it back 300 times. So what we're asked is to find the chi-squared value that we draw a red marble 5 times more than a white. And you can see that because we have 5 times as many, right? We have 5 times 1 is 5, so 5 times as many reds as whites. So we want to test to see if that's actually true. So our H null is that we do have 5 times more, and the alternative would be that we do not have 5 times more. And again, the alpha level, which I haven't really showed, but we're just doing this at our normal standard, which is 0.05. So this is what the observation table looks like. We have red, yellow, green, and white. So we expect this to be split out accordingly, which would be out of 300, we would expect 125 reds to be picked, 75 yellows, 75 greens, and 25 whites. So if you times 25 by 5, you'd have 125. So this is what we expect. What we actually observed was 110 reds, 73 yellow, 82 green, and 35 whites. So that's what we observed happening. So if we were to calculate our chi-squared, this would be 110 minus 125 squared over 125 plus 73 minus 75 squared divided by 75, so on and so forth. So you just take each one paired up with its observed and expected. So when you do this calculation, our chi-squared value is equal to 6.506, and we have degrees of freedom. We have 4 categories, so we take away 1, so that's equal to 3. So using this information, let's jump over and find our chi-squared critical value. So we had 4 minus 1, which put us at 3 degrees of freedom at 0.05, which gives us a critical value of 7.81. So coming back over here, we know that our critical value on the chi-squared test is 7.81. So anything beyond that is the rejection region. And in this case, turns out our critical value is actually further away. So we actually observed a 6.506 value, which tells us that we do not reject the null hypothesis, and we conclude there's not enough evidence. So there's not enough evidence to say that red is not drawn or picked 5 times more than white. So what is this saying? Well, it's saying that we're not saying that it doesn't get picked more than 5 times than white, but we're also not accepting that it does get picked 5 times more than white. And that's how statistics works. Check out my hypothesis basics video if you're unfamiliar with how to write conclusions. But basically, we're not accepting the null hypothesis. There's just not enough evidence to reject it, if that makes sense. So what we try to do with hypothesis testing is we would like to see the alternative hypothesis come true or have evidence to support it, because that's what's interesting. In this case, because we're not in our rejection region, we can't reject the null hypothesis. So that's what we're saying here, is we do not reject the null hypothesis, and we're concluding that there's not enough evidence to say that red is drawn 5 times more than white. So that's how that would be written in this case. So these are just a few chi-squared example problems. I hope that this is helpful for you guys with the questions that you're coming across. As always, guys, leave any comments of problems or topics down below. I'd be happy to make a video for you. Make sure to hit the like and subscribe button, and we'll see you in the next video.